All right, so today is the last day with new content before the test, before test number 1. So as I said last time, make sure you test yourself on the key terms before Wednesday. Any outstanding questions, we can discuss them then. Obviously there won't be a quiz that day because there's no new content. But today we'll be covering two different things, scientific realism and Bayes' theorem. And I want to say up front, even though I've put them in the same lecture, there's no real connection between them. You could maybe make one up with some effort, but it's just the two outstanding things I wanted to discuss, so you can think of today as like miscellaneous day. One thing I wanted to note, I deleted a few terms from chapter 6, so just download the most recent version. It's not relevant for today, but some of the terms were only in the old edition of the book, which I originally made the key terms from. So have a look at that. Don't worry about the terms that are only in the old version. Additionally, some of you may have noticed that I re-uploaded the video yesterday, the Thomas Kuhn one. There was an audio glitch in the second half of the video, like the video recording must have paused for a second, so then it was all out of sync. If you ever notice anything like that, just let me know, and the sooner the better, because my iPhone has limited storage, so I usually have to delete the recordings before I film a new one. So if you ever notice something like that, just let me know. It'll make it easier to fix. And with regard to last class, one thing I forgot to mention is Godfrey Smith, author of the textbook, has a really nice discussion of Theorem, specifically his argument that since there can be no rule book or official guide for when to give up a theory or a paradigm, that there's no strict set of necessary and sufficient conditions, therefore anything goes. That's Theorem's argument. Since there's no rule, therefore we just kind of make it up, and there's no rational basis for deciding. And Godfrey Smith has a great discussion of this, saying that that's a very unreasonable inference. In most cases where we know what the rational thing to do is, or where there are good rules of thumb for what's rational to do, there are still exceptions. So one nice example is, and Godfrey Smith has a similar one, is buying life insurance. Buying life insurance is, as a general rule, a rational thing to do. If you're the you have a family, let's say you're the sole money maker, it's rational to put money into life insurance, even though it may turn out that your whole family gets hit by a bus, you outlive your family. Okay, it turns out it was the wrong decision, not in retrospect, but that doesn't mean it's not, as a general rule, a good idea to buy life insurance. And you could say the same thing about rules of thumb in philosophy of science. They're not going to be exceptionless, they're just good general rules of thumb. So Godfrey Smith has a good discussion of that I forgot to mention. Okay, so let's get started on the chapter on scientific realism. So I'm going to start actually just by reading the first two paragraphs. They really give a good sense of what the two competing intuitions are. So the first paragraph gives kind of the realist intuition. What does science try to describe? The world, of course. Which world is that? Our world, the world we all live in and interact with. Unless science has made some very surprising mistakes, the world we now live in is a world of electrons, chemical elements, and RNA molecules, along with other things. Was the world of 1,000 years ago a world of electrons and RNA? Yes, although no one knew it back then. So that really captures the scientific realist's intuitions. One way of saying what realism consists of is it consists of the claim that the truths of science are objective, or as Godfrey Smith calls it, mind independent. Now he adds a qualification to this, but I won't talk about that right now. To say that a truth is objective is to say that it's true whether or not anyone believes it. So if you're a scientific realist, you believe that it was true that the Earth orbited the sun before anyone thought that was true. The truths are independent of what we think. as opposed to a subjective truth or subjective claim where it is dependent on what someone thinks. So for example, to say that ice cream tastes good is not really something that's or vanilla ice cream tastes good. That's something that's true in virtue of how we react to it. It's true in virtue of what we believe about it. It's not mind independent. Of course, there's a debate in ethics about what kinds of truths are moral truths. We won't get into that. But if someone was a realist about morality, that would mean they think moral statements can be true or false independent of what a culture says or what people say. Okay, so that's the realist view. The second paragraph captures well the alternative. The concept of an electron is the product of debates and experiments that took place in a specific historical context. If someone said the word electron in 1000 CE, it would have meant nothing, or at the very least not what it means now. So how can we say that the world of 1000 CE was a world of electrons and RNA? We cannot. We must instead regard the existence of these things as dependent on our concepts, debates, and negotiations. So there's the debate. There's the two perspectives. On one perspective, scientific truths are independent of us, and on another, they are relative or dependent on our conceptions. So the book talks about the idea of common sense realism. You can think of common sense realism as an umbrella that would include scientific realism. So common sense realism is just the view that reality exists independent of us. There are objective truths about the world. And scientific realism is the claim that science gets at that objective reality, gets at what's true. Now, as I say, though, Godfrey Smith points out that this is a little bit tricky. You have to be kind of careful with this idea of mind independence. What a common sense realist and a scientific realist will want to say is, things like the sun and the moon and the animals, their existence does not depend on what we think about them, or truths about them don't depend on what we think about them. But presumably there are truths that are mind dependent. For example, there are facts about our minds, about what our minds are made of, what their basis is, and that's not strictly speaking a mind independent thing. It's a fact about the mind. Similarly, our minds, whatever they are, and that's the subject of the second half of this class, but our minds have effects on the world. So the fact that this building exists is in part because people sat around and had ideas to build a university. So Godfrey Smith has a nice modified definition of common sense realism, which is we all inhabit a common reality which has a structure that exists independently of what people think or say about it, except insofar as reality is comprised of or causally affected by our minds. So that's a nice caveat he adds, but other than that, the world, on the realist perspective, is mind independent. And then scientific realism is just the claim that science accurately describes that reality. So, is there any argument for accepting this perspective? Why should we be scientific realists? By far the most influential argument for scientific realism is the no miracles argument. Godfrey Smith doesn't do it this way, but you can put this actually as a deductive argument. And here's how you would do it. So premise one, mature scientific theories enable us to make accurate predictions. Now, no one denies that, right? No one's going to say, no, it doesn't enable us to successfully predict what's going to happen in our experiments. Like, that's just, no one but a crazy person is going to deny premise one. Premise two it would be a miracle now I can't write the full premise, but it would be a miracle if, basically if premise 1, if mature scientific theories could do this without being at least approximately true. So scientific theories enable us to make predictions with a high degree of precision, and it would be, premise 2 is, it would be a miracle if they could do that without being true. And just to give you one example, it's not a video, just some text. I don't feel like writing this many numbers on the board. I'm not going to go into too much detail here. This might take a second to boot up. I forgot to do this at the beginning. Okay, so while that loads, okay, good. So, in quantum mechanics, there's an idea called the magnetic moment of the electron, which, again, you don't need to know, but basically what it is it's how much of a magnetic field is generated by an electron spinning. So based on quantum theory, this is what you predict the magnetic moment of the electron will be. So it's 1 point, very precise number, plus or minus 30, which would go about here. And the error bars are based on approximations and idealizations in the theory. So there's some things you have to kind of gloss over when making this prediction. And then you measure it with an error bar of about this based on measurement error. And if it's hard to read it, it's the same up to here where it's 0.188 compared to 201, which is within the margin of error. So magnificently precise prediction that's confirmed by experiment. So there's an example. So how is quantum theory able to do that? Well, premise 2 says it would be a miracle if it could do that without being true. It would be very surprising if it could do that without being at least approximately true. And then premise 3, there are no miracles, at least not in science. And none of the anti-realists want to appeal to miracles, so that one they'll probably accept too. And so conclusion, you have to kind of think about how this deductively follows, but you'll have to take my word for it. Deductively, it follows that mature scientific theories are at least approximately true. So that's the no miracles argument spelled out deductively. Any questions about what these premises mean before I say more? Okay, so that's putting it deductively, but I have 2 short video clips of Richard Dawkins giving a kind of punchier version of the no miracles argument. So if we can get the lights, I'll show that as well. Okay, so as I say, a little bit of a punchier, not as rigorous version of it, but that's basically the no miracles intuition. That, look, science enables us to make these accurate predictions, and that counts as a reason to believe that it's true, or at least approximately true. So maybe we should go home. That seems pretty compelling to me. Is there any reason to doubt this picture? Well, one reason that the book mentions, we saw, I guess on the first day of class, in some sciences, it's not clear what it means to assert that the theories are true. So one example is quantum mechanics. So even though, yes, it enables us to make accurate predictions, what does it mean to say that it's true? Because it says really spooky things like an electron can be a wave in some context and a particle in another context. And some people have taken that to mean that asserting realism is a kind of, is unnecessary. You don't need to, and actually unclear what it would even mean to say that the theory is true. One solution that I'm going to offer towards the end of class, the book mentions it without mentioning the name. It mentions the guy who came up with it, John Worrell. The name for Worrell's position is structural realism, where what's real in a scientific theory, or what we should be most confident is real, is not the entities like electron or gravitational force, whatever, but the patterns or the mathematical structure. As I'm going to say later, those tend to be what survive across theories. So, Einstein's theory has a very different picture of the way the world works, but many of the mathematical patterns are the same. If that doesn't totally make sense yet, you can just hold that thought, because I'm going to say more about that towards the end. One source of motivation for rejecting scientific realism is various types of empiricism, especially very strict kinds of empiricism. So on the first day of class, we saw one example of an empiricist philosophy of science that rejects realism, which is positivism. Right? In positivism, the goal is not to get at the hidden structure of the world. The goal, you just stick to what's directly observable. An older and kind of crazier empiricist view that is incompatible with scientific realism is idealism. I'm not going to spend as much time on this. We're actually going to come back to it in the philosophy of mind section. So this comes from the empiricist George Berkeley. Have any of you heard of this? And we've taken a philosophy class, idealism, one wavy hand, or two. So this is the view that matter does not exist. All that exists is conscious experiences. This may sound very crazy, but if you want to make yourself kind of freaked out, you can. If you reflect on this, it becomes not so crazy. So, in the standard way of thinking about things, the common sense realist way, this marker is an object that exists whether or not I'm looking at it. It's made of atoms, etc. But someone like Berkeley would say, no, what exists is your experience of the marker. That's all you can know for sure. All you can know is, I'm having a black marker experience, so to speak. And what Berkeley says is that's all that exists. There's no such thing as matter. And then you may wonder, well, what happens when I'm not looking at the marker? And Berkeley says God is looking at everything all the time. So everything exists as an experience in God's mind when we're not looking at it. So that's kind of, well, that shouldn't be me, but I think that's a little bit goofy, but that's Berkeley's view, which is motivated by empiricism. And what many 20th century empiricists said is, it's not that they endorsed idealism, but they said the distinction between idealism and materialism or realism doesn't matter. All that science should do, as there's a quote here from Schlick, which says, what the scientist seeks are the rules which govern the connections of experiences and the rules by which they can be predicted. So we have conscious experiences. What are the rules by which they're related? If you see this, then you will see this after. Don't theorize beyond that. Don't theorize about what's really going on. Just stick with the patterns in what you observe. And today, the most important, so positivism, as we saw, fell out of favor. And for a long time, anti-realism fell out of favor along with it. People thought, well, positivism is dead, so scientific anti-realism is dead too. But almost single-handedly, a gentleman named Bos von Frossen made scientific anti-realism respectable again. The term for his view, and there's a Stanford Encyclopedia of Philosophy page that I have on eClass that you can look at. The name for his view is constructive empiricism. don't worry about that term. We're just going to call it Bos von Frossen's view. Godfrey Smith, the author of the textbook, says that it's useful to think of his view as a type of instrumentalism, which is roughly the view that the goal of science, or what science should be, is a set of tools for making predictions. And the term that von Frossen uses is that a scientific theory should be empirically adequate. And von Frossen knows that theories often invoke things that you cannot directly observe. And what he says about those is it's perfectly fine to use them, but all that matters is whether your theory explains all of the available evidence. That's what empirically adequate means. All the relevant evidence in a given area should be able to be explained by the theory. Now, does that mean the theory is true? Does that mean that quarks and fusion inside the sun really exist? Von Frossen's going to say, don't ask questions like that. If it explains the data, that's all you want out of a scientific theory. You should aim at no more than that. And I'll say, that is a defensible view. It's not a view that I think is, it's not the perspective I would take, but it's definitely a defensible view. One problem with it that is not a knockdown argument against it, but it's something that someone like von Frossen's going to have to deal with, is the line between what you can observe and what you can't is kind of a feature of what technology we have at the time, and the line often moves. So, so let's say here, this is the line right now for between what we can observe and what we can't. So, here we might have in earlier stages of science, things like molecules would have been, unobservable, and then, patterns in, the behavior of water. Let's say we're dealing with water, right? So that you can see. And scientists postulate molecules as a way to explain what you see. And von Frossen says, okay, we're not going to comment on whether these exist because they're unobservable. But as technology improves, this line moves, of course. We develop better microscopes, better ways of measuring things. And actually, in some cases, it's not clear what counts as observable or not. Like, does an electron microscope count as seeing something? Well, okay, a little bit fuzzy. And what Godfrey Smith says is it's kind of arbitrary to draw the line at of what we should believe in at where technology happens to be now. Because of course today, molecules are, at least you could make the case that they are observable. And so then, at a finer grain of detail, things like quarks you can't directly observe with current technology. So von Frost is going to say, okay, therefore we shouldn't believe in them. Something seems a little bit arbitrary about that. Not saying that's a knockdown argument against the view, but it's something to think about. The next section, actually, I guess before I move on, since he's very important, any questions about Bos von Frossen? Oh, I forgot, actually, I have a video of Bos von Frossen. We live in a very privileged time where we can see videos of these people talking, so to add a bit of extra oomph to this, I have a video of von Frossen explaining his view. Okay, so the next section is on metaphysical constructivism, which is the view according to which, and at least at a first pass, it's kind of hard to make sense of a view like this, but that our theories in some sense create the world or change the world. So Kuhn, on a kind of literal reading, would be an example of this, right? Remember we saw last time that Kuhn argued that when theories change, the world changes, which is basically a way of saying, there is no mind-independent reality. We can only speak of reality as viewed through a theory. Now, at first glance, that seems pretty crazy, and I do think it's crazy, but the book discusses a way of making it maybe slightly less crazy. And this draws on a distinction that Immanuel Kant made, one of the most important philosophers, 1700s. And that distinction is between the noumena and the phenomena. These are both plural. The word phenomena is more commonly used. So noumena means things in themselves. So this is what presumably the scientific realist is after, right? How things really are, whether or not anyone believes anything about them or looks at them or whatever. So the way things are in themselves. And then the phenomena are things as experienced by us, or how things appear to us. So, like an example of phenomena is, this blue marker. As we'll see in the philosophy of mind section, there are lots of problems related to this. So to me, it looks like, it has a certain shape, it's blue, at least in parts. But when you try to think about the noumena, it's not clear that, the thing is blue in itself, right? Atoms aren't colored. It's just that light bounces off it in a certain pattern when it hits my retina and goes into my brain. To a first pass, it's I'm having kind of bluish experience when I look at it, but it's not blue in itself. If that example gives you trouble, you can think about how things, taste to us, right? So that would certainly be an example of something in the phenomena category, right? So this is kind of an absurd example, but if you ever go on a camping trip and do your business outside, you leave something behind, what you will see is insects eat it. So to them, it tastes good. Now, and we will say, no, obviously to us, it does not taste good. It's not as if we are right and the insects are wrong, right? Taste is just about how we react to things. It's about how the thing is experienced by us. It's not tasty or not tasty in itself. It's not a part of the noumena, so to speak. So Kant makes this distinction, and he thinks that many things that we take to be a part of the noumena are actually a part of the phenomena. They are only a part of how we experience the world. Kant thought that our mind had a certain structure and that it shapes how we experience things. So things like the passage of time, Kant thinks that's not a feature of the world, and if you assume that it is, you run into all sorts of paradoxes and complications. So there's no time in the world in itself. That's just how our mind structures our experience. That's one example. So this is a very influential distinction in the history of philosophy. There's something similar that Popper says, right? When Popper says, all observation is theory-laden, he means that you can't observe things without your mind shaping how you observe it, without features of what you think shaping how you observe it. So one way of making metaphysical constructivism less absurd is to say it's not as though making new theories changes the noumena, but it can change the phenomena, how we experience the world. That's maybe a less crazy way of saying it. Now, I still don't want to quite say that, but what Godfrey Smith says is what metaphysical constructivism reminds us of, and actually Popper says something similar, is theories are not passively created by looking at the world. It's not as though, this is what the positivists thought, you just look at the world and the world kind of forces itself upon you, and the theories are kind of just blindly built up out of data. But in fact, theory creation is an active, not a passive process. Popper, in the book that I have recommended, says, it's not the case that the truth is obvious, that if you just look at it carefully, it will just present itself to you. It's a creative, active act to create a theory. It's not just passively taken from the data. Okay, so those are some different, before what I said about Popper, those are some different types of scientific anti-realism. Is there any argument for taking this view? What are some reasons for not being a scientific realist? there are different considerations, but by far the most influential argument, there's different ways of saying it, but they fall under what's called the pessimistic induction. It's sometimes called the pessimistic meta-induction. I don't know, philosophers like making things sound cooler than they are, but pessimistic induction is fine. So remember that induction involves generalizing from a set of examples or particulars. So we saw that before the Popper chapter. I assume you all know what pessimistic means. And here's the way this, so it's the pessimistic induction from the history of science. And what people who make this argument observe is that throughout the history of science, there have been theories which we had a lot of evidence for that made lots of successful predictions, but then turned out to be false. So we've seen lots of examples of this. One example that I said we'd be coming back to again and again is the transition from Newton to Einstein. So Newton's theory has lots of postulates about the way the world works, like that there's absolute space and absolute time, that gravity is an attractive force that operates at an instant and at a distance. And this theory led to lots of successful predictions, right? It explained, or to use von Frost's term, it was empirically adequate. It explained almost all of the data. And so if you were using the no miracles argument, you would say, well, Newton's theory must be true, because it would be a miracle if Newton's theory enabled you to make predictions, but without being true. But that's exactly what it did, because we know that Newton's theory is wrong. And now there's a wider range of data, and we know that Einstein's theory is at least, well, I can't say more true, but it explains more of the data than Newton's does. And it doesn't have things like absolute time or action at a distance or things like that. So those features of Newton's theory we know to be wrong. And so pessimistic induction, the induction part is generalizing. So we should have no confidence that our current best theories are true. Basically, how do we know we're not in the same situation that the Newtonians were in? So we say, look, quantum mechanics, evolutionary biology, relative, whatever your favorite theory is, it explains all this data, so it must be true. Well, that's exactly what the Newtonians said. And it turns out Newton's theory is wrong. So how do we know we are not in that same position? And in fact, if we use induction, we should bet that we're in that situation, if you're willing to engage in induction anyways. So these are both, so we're kind of stuck. We have two arguments, both of which seem quite compelling. Yes?
Like, the key thing that you've been saying is that it's like approximately true?
Yeah.
So how could they use the pessimistic induction to disprove like Newtonian when it still is used today like to describe motion?
Perfect, yeah, exactly. So this is going to be part of the solution. So part of the solution is to cash out that idea of approximately true. To say that, yes, Newtonian theory is still approximately true, as you say. It's still used to explain lots of data, make predictions. It's just not the final truth. So this is kind of where I'm heading with this. The view that I think can absorb the pessimistic induction and still be supported by the no miracles argument is structural realism, which I already mentioned, but we'll try to cash it out a bit more. What structural realism says, and there's different versions as I'm going to say later, but to a first approximation, it says that the parts of scientific theories that are real, or that we should be most confident are real, are the different ways of saying it, the mathematical structures or patterns or relations. So in the case of Newtonian gravity, the fact that objects fall according to the inverse square law, that's a kind of mathematically describable pattern that is still true in Einstein's theory, right? Even though the kind of many of the features of the kind of semantics of the theory, like an attractive force or absolute space, absolute time, those we no longer accept. But many of the patterns described by Newton are still true and used. And the reason that works is Newton's theory within certain domains of applicability is actually a consequence of Einstein's theory, right? As long as you're not moving too fast and things like that, Newton's theory is still can be predictably successful. One way to think about this might be a little goofy, but may help. If we think about Kuhn's example, oh, you don't need to. Sorry. This is just a picture. So remember the duck rabbit. So what the lines of white and black are depends on what your theory is or what gestalt you're using. So the lines up here, if you think it's a duck, those are going to be part of the beak. If you think it's a rabbit, they're going to be ears. And what a structural realist will say, obviously this is just a toy example, but what's real are the patterns in the lines, right? Those stay the same across theories. In the case of science, as long as the patterns are well replicated, they will very likely survive theory change. But what those are is what changes. Are they, is gravity an attractive force, or is it curved space-time? That's going to depend on the theory. So you can think about this in relation to theories in psychology. So, are the things that we study real? So think about like the big five, right? So the big five, people might ask, are those real? Is something like extroversion real? And the way we discovered the big five is, as I'm sure you all know, you do factor analysis. Maybe you repress this, I don't know, but you would have been told in your intro psych class that you use factor analysis. So you give large batteries of personality questions, and you look at how those questions correlate with each other. So, and you can then put them into factors. So questions like, do you like going to parties? Do you have lots of friends? Do you have a lot of energy? Those all tend to go together. They all tend to correlate with each other. People who give high answers on one tend to give high answers on the other. And so we call that, clump, this is one way of representing it. So that clump of questions that kind of go together, we call that extroversion. And if you put those into a scale, those questions into a scale, you can use that to predict future behavior. Now, a certain kind of realist may ask, okay, but is extroversion real? And if you're a structural realist, you'll say, well, yeah, it's a real pattern, right? The kind of catchphrase from the structural realist is to be a real pattern, right? A pattern that's well replicated and that enables you to make predictions. That's what counts as real. This view somewhat muddies the line between scientific realism and anti-realism. And one way of bringing that out is to think about Bos von Frossen. So I've not read all of Bos von Frossen's book on the subject, but I had a look at the chapter on scientific realism, and I was curious what he had to say about the no miracles argument, which is kind of the best argument against scientific anti-realism. And here's what he says. This is how he responds to the no miracles argument. Any scientific theory is born into a life of fierce competition, a jungle red in tooth and claw. Only the successful theories survive, the ones which, in fact, latched onto actual regularities in nature. Now, that sounds kind of realistic, right? So, in fact, latched onto actual regularities in nature. So that's the sort of most recent, most well-developed version of anti-realism. And then, so it says that science latches onto actual regularities. And then the most advanced version of realism says the goal is to find real patterns. Now, you could write a PhD thesis trying to distinguish those, but not all that different. Now, there is a distinction between two different types. of structural realism, epistemic and ontic, or you could say metaphysical. Ontic means ontological, which is basically the same as meta. It's about what's real. Whereas epistemic relates to epistemology. So epistemic structural realism says, actually I guess before saying that, I should contrast this with, or I should say what's missing from this compared to the standard versions of scientific realism. The standard versions of scientific realism want us to believe in the existence of like the things in a theory, quarks, electrons, or whatever, and say that we know those are real. And a structural realist is kind of uncomfortable with saying we know the intrinsic nature of these things. And when you push an old-fashioned scientific realist, you can make them uncomfortable by asking, okay, you say electrons exist. What are electrons exactly? And then it gets pretty complicated pretty fast. So it's not even clear what it means to commit to the existence of things like that. So going back to this distinction, what an epistemic structural realist will say is, there may be things with an intrinsic nature, but all we can know is the mathematical relations. We can know the patterns and how things are related, but we can't know what their intrinsic nature is. Whereas the ontic or metaphysical structural realists go the next step and say, all that exists is the mathematical structures or the relations. So it's kind of a stronger version of structural realism. So there's more to be said about this. In the optional videos, I have listed 2 podcasts with the philosopher James Ladyman, who has, which is kind of funny last name, but he has worked this out in more detail. But I have a video of John Worrell, who actually developed structural realism. Now, before I show it, I just want to say that, so the example he talks about, we're not going to see the whole video, he talks about the transition between Fresnel and Maxwell. Very simply, Fresnel thought that light was vibrations through a medium, whereas Maxwell's theory says there is no medium. So again, a very different picture of the world, but what the guy will see, what he points out is the mathematical structure is very similar. So this is a good way to put a fine point on the structural realism idea. Now, at the end of it, he plays a song that he and his band wrote. I will only play that for like 1 second because it's very funny. If I play it it's like looking at the sun. If you look for too long, it's like painful. And if you listen to the song for more than 2 seconds, the cringe is just, it's too much. The name of the band is kind of cringe too. It's a critique of pure rhythm, which is a play on Critique of Pure Reason, which is a book by Kant. So that's pretty, so I'll only play that for like 1 or 2 seconds, but it is kind of funny. And before that, he explains structural realism a bit more. So if we can get the lights. Okay, now, so what do we take away from this? Does this mean that scientists are wrong to put forward theoretical accounts at all? Shouldn't we just be focusing on putting forward mathematical models? Personally, I don't draw that implication. I think that theorizing about what's really going on is a useful way of developing new ideas and new models and new predictions. It's just the theoretical part is not what we should be most confident in. What we should be most confident in being real is the mathematical structure or the relations. So one useful example from psychology of a pattern surviving theory change is different types of conditioning. So just as a kind of toy example, so think about Pavlov's dogs, right? So you ring a bell, give the dog food, ring a bell, give the dog food over and over again, and you measure, so let's say this dotted line is, is the point at which you stop giving the food. So after the dotted line, you start just ringing the bell. Before the dotted line, you ring the bell, give the dog food, ring the bell, give the dog food. And then you measure how much the dog salivates in response to the bell before the food is presented. And you find, as you all know, that the amount that the dog salivates goes up with these repeated presentations. Then if you stop reinforcement, you find that the amount, and then you repeatedly ring the bell without the food, the amount of salivation in response to the bell goes down. So in behaviorism, this is conceptualized as a kind of mechanistic automatic reaction that this association is made. Whereas the cognitive people, and there's some reason to take this seriously, so cognitivism of course comes after behaviorism, they will say that what's happening is the dog is forming an expectation. It's forming the expectation that when the bell is rung, food will come. One piece of reason for thinking that is that there are studies both with humans and animals where when you block awareness of the neutral stimulus, the association does not form. There's various other arguments that they make for concluding that what's actually going on here is information transfer or the forming of expectations. But notice, this is still right? The pattern that the behaviorists found is still right and is still true even in the cognitive paradigm. So there's an example from psychology. Okay, so there's one more section in that chapter on natural kinds, but any questions about structural realism before I move on to natural kinds? Okay. So natural kinds, so there's, well, in a technical sense, there's an infinity of different ways that we could categorize things. So we put things into categories, right? And there's different ways we could do it. In a technical sense, there's an infinite number of ways we could do it. The idea of natural kinds is that there are some ways of categorizing things that are more accurate, more true to the world than others. So you kind of have to be a scientific realist to take natural kinds seriously. One phrase that is sometimes used to describe natural kinds is, we want to carve nature at the joints. So if you're carving an animal and you want to cut it up at the joints, and the idea is when we're making categories, electron, rat, planet, we want to do so in a way that corresponds to how things are actually clustered in the world. So that sounds right. And just to motivate this, so one silly example that James Ladyman gives is, you can make the following category: my left earlobe, the Eiffel Tower, and the largest elephant in Africa. And nothing stopped me from doing that, but presumably if I make a category like that, it's going to give me no purchase on the world. By grouping those things together, I gain no insight or no ability to make predictions. Whereas a category like all oxygen atoms does give me a better purchase on the world and enable me to make predictions. A view according to which the idea of natural kinds, I guess that's opposed to natural kinds, is nominalism, according to which categories are entirely made up by us. The world is just the world. It doesn't come pre-made with categories. And nothing makes one category more right than another, except maybe human interests. We may be, it may be useful to us to categorize things in a certain way, but the world does not come pre-packaged with categories. They are entirely made up by us. There may be a way of reconciling a sense of the term natural kinds with this, but to a first approximation, that's what that view commits you to. One complication that I'm not going to spend too much time on, but I'll just explain what it says in the book. So this was in the quiz. The distinction between interactive kinds and indifferent kinds. All this is getting at is the fact that, look, sometimes the act of categorizing affects the things that fall under the category. So in psychology, virtually all of the categories we have fall in this bucket, at least potentially. So, when you classify people as being schizophrenic, which is the example the book gives, you will actually change. You can make people think of themselves differently, which could in turn affect their symptoms. When you classify them as being schizophrenic, you make it more likely they will receive medication, which could in turn affect the phenomenon. So that's an interactive kind. Whereas something like, an up quark, I think that's the one with 2/3 of a positive charge. No matter what up quarks will be like that forever. Categorizing that doesn't make them think differently about themselves or change what they are. So things that fall under indifferent kinds would be like that. They're not affected by the act of categorization. And then the last term for the scientific realism chapter is eliminativism, which comes from the word eliminate. So eliminativism, there's eliminativism in different areas, is the view that a particular categorization should be gotten rid of. It does more harm than good. It doesn't help us make predictions in a useful way, so we should dispense with it. So one example that the book briefly talks about is race. Right? There's an argument to be made that given that differences at the genetic level are so small, it's not useful to categorize people in that way. That would be one example. One that we will see in philosophy of mind is there are some people who say that ideas like consciousness are so fraught and unhelpful that we should get rid of them. That would mean being an eliminativist about consciousness. Pretty radical view, which we won't address right now, but that's what eliminativism means. And that is the last thing I have to say about the realism chapter. Any questions? Yes?
What did you say that interactive kinds meant?
Interactive kinds means the things that fall under the category can be affected by the act of categorizing. So think of schizophrenia as an example. Yeah. Any other questions? Okay, let's take the break. Let's come back at 12:50. All right, let's get started again. So camera's on. Good. Okay. So I forgot that I actually had a few other closing thoughts on the realism chapter. I'll say those and then we'll get into Bayes' theorem. So one thing that I think structural realism would require us to give up, even though it's a very tempting idea, is the requirement that we have to be able to visualize what things are or grasp what they are in intuition, right? So when you think about particles or quarks or whatever, because we are so visually oriented, it's tempting to think there must be some kind of three-dimensional object down there that we can visualize, but our intuitions about 3D space may be something that's just a part of how we perceive the world. So that's one cost of the view, but that's probably something we would have to give up. And one other thing I wanted to add, just to make it more precise what it means to be a pattern. One way that Dan Dennett has put it, so I've mentioned Dan Dennett a few times, he's going to be arguably the main character of the philosophy of mind section, and he's the one who coined the phrase real patterns in a paper he wrote. And one way to think about it is, if you can save how much data you need to describe something, then there is a real pattern. So if there's an image on the computer and you have to save in data, like what the image is, if it's pure randomness, it actually takes much more data to save it. But if there's like a patch of blue or something, this counts as a real pattern because you can save it with less data. You can just say blue over there. Whereas if it's totally random, it takes more data to save. There's no data saving method. So if you can save how much data you need or how much information you need to describe something, that counts as a real pattern. This is going to be very important in the section on Dennett, where he talks about his different stances, like the intentional stance and the design stance. But that's just a teaser. We'll have to wait for Dennett to see that. So now we move on to the chapter on Bayes' theorem. As I say in the key terms, if anything here looks scary, I encourage you to not be scared. We're going to go through this carefully, and I think it's a very useful way of thinking about science, and actually a useful way of thinking about how you gather evidence in everyday life. So remember back in chapter 3, we saw that attempts to create an inductive logic failed, that there was the positivists and various others tried to make an inductive logic that's comparable to deductive logic. And of course, Popper is very happy with this failure because he thinks we shouldn't be using induction or probabilistic reasoning at all. We should just be engaging in conjecture and refutation, just trying to prove ideas wrong. But Popper is pressed to say, well, what do we do about the theories, or what do we say about the theories that have been well tested and have survived the tests? And his term that he puts forward is corroboration, which is pretty weak. All it means is the theory has survived attempts at falsification, but it doesn't mean that we can say the theory is more likely or probable or anything like that. And that seems wrong. It seems that we want to be able to say something more than that. And probably the most popular way of cashing out a probabilistic method of inference is Bayes' theorem. So we're going to build up to it, though. Before we look at the actual equation, we're going to have to work our way up. So the fundamental thing that you have to give up, that's a very common sense way of thinking about things, is thinking of belief as on or off. You know, people ask, do you believe X? And you're supposed to say yes or no. If you're a Bayesian, that's the first thing that's got to go. Bayesians don't speak of belief as an on or off thing. It's on a range. You can do it from 0 to 100% if you want in your head, but the way they do it is 0 to 1. So there's different ways of talking about this. You can speak of your degrees of belief or degrees of confidence. Or the way they sometimes put it is, what's your credence in X? Where credence is something that is on a range from 0 to 1. So 1, having a credence 1, would mean you are completely certain that the proposition is true. So some candidates, so Descartes has a credence of 1 in the sentence, I exist. He thinks that you can have credence 1 in that. Or, 7 times 3 equals 21. Maybe we should have a credence 1 in that. Now, if you're Quine, maybe you say 0.9999. Maybe you say that it's at the center of our web of belief and we're very unlikely to change it, but you can imagine a situation in which you would. But certainly your credence is going to be as high as it can be in a sentence like that, or in a statement like that. A credence of 0 would be certainty that it's false. So presumably most of you have a credence of 0 or close to 0 in this equation. 7 times 3 equals 29. Probably you'll have a credence 0 or close to 0 in something like that. And 0.5 would mean perfect agnosticism. So take the sentence, Donald Trump will be president again. God forbid. So my credence in that sentence is 0.5. He's ahead now, you never know, coin flip. Maybe a little more, a little less, but it's certainly around there. That would, if I was going to be betting, I would bet close to 50-50 in the sentence, Donald Trump will be president again. And then you can have, of course, everything in between. So probably for empirical statements, you never want a credence of 0. So the sentence, the earth is flat, my credence is probably 0.000001. Not quite 0 though. Maybe I've been lied to my whole life and all the pictures are fake. I would never bet on that, but maybe not quite 0. And then a sentence like, William Shakespeare wrote Hamlet, maybe 0.9 or 0.95. There's some fringe historians who say someone else wrote it. I don't know for sure, maybe 0.95. So those are just some examples to give you a sense. Now, you may say, okay, that all sounds nice, but how do you cash out these numbers? You just pulled those numbers out of the air. Like, can you make them more precise? And the way that Bayesians try to make these numbers more precise and measurable is in terms of bets. What kinds of bets would you be willing to make? And so you have to assume that people like making money. If you assume that and a few other things, you can take betting behavior as a measure of how confident someone is in a statement. So take the sentence, I'm stealing this example from Juliet Galef, who I'm going to be showing a video of later. Take the sentence, there will be self-driving cars available for purchase in Alberta by the end of the year. Does anyone think that's true? No. Okay, so now presumably none of you have a credence of 0. Like it's conceivable that that could be the case. And you may think, well, there's no way I could put a number to that. How could I put a number to how confident I am that there won't be those driverless cars at the end of the year? And one simple way to do it is just, suppose I say, I want you to make a bet, and if you do this, if you're right, I'll give you $10,000. But I'm going to give you a choice of 2 different bets, and you have to choose which one. So one is there's a box with 4 balls. One of them is black, 3 of them are white. You can't see inside. And then we have the sentence we're considering. There will be driverless cars in Alberta by the end of the year, available for purchase. And so I tell you, which of these bets would you rather take? So, and then you pick one, and so this means you are less than, you think there's a less than 25% chance that this is true if you'd rather take this bet. And then you can just increase the number of balls until you go, so in Galef's example, once it got up to, I think it was like 10 white balls and 9 white balls and 1 black ball, she's like, I'm not sure which bet I would take. Once you've reached that point where you're not sure which bet is a better bet to take, that's a measure of how confident you are. So if you're in that position, your credence in this is around 0.1, around 10%. Because when forced to choose between a bet that you know is 10% and this, you're unsure which to take. There's other ways of doing this, but all of them involve betting behavior. That's how the Bayesians operationalize your credence or degree of confidence in a sentence. Okay. Now we're going to do another activity, or I guess this one isn't really an activity. So if you have a computer, log into eClass and go to the announcements, and you'll see, I'll put it on the board too. Oh, the projector resurrected.
Okay.
So. If you don't have a computer, you can follow along here. So here's what you're going to do. So for, you can write this down on a piece of paper and make sure you write down the numbers, like 1, 2, 3, etc. So write this down on a Word document or a piece of paper. You have to write down 2 things for each number. One is true or false. You have to write what you think the sentence is. And then how confident you are on a scale, 55 to 95. We're going to be doing something with this information. Basically, the point of this is to see how well calibrated your confidence is. Is it calibrated to how often you're right? So for each one, select one. So the way it works, if it's 55, you're basically guessing. If it's 95, it's like, no, I would bet a lot of money that my answer is correct. So go ahead and do, does anyone not have a device with them? Okay, so I don't need to have this up then. So just do that, and I'll check in and see how we're doing, and then we'll go from there. So once you are done, you can scroll past the graph in the middle. At the bottom are the answers. So then you can mark them, and then once you've marked them, we'll be doing something with that. So that's the next step. Is once you've finished all 40, go ahead and see which ones you got right. Okay, has anyone done marking? So the final step, so those of you who are done marking can get started on this, is in the middle you'll see that table. Column A is number of times you were right, column B, number of times you were wrong. And what you have to do is put those numbers in for each of the percentages. So how often were you right when you were only 55% sure, and how often were you wrong? And then you can calculate how often you're right. So when you're, and presumably it should be, if you're well calibrated, it should be closer to how sure you are. And then you can plot it on that scatter plot. So the x-axis is, what I have on there is the x-axis how sure you are, so 55, 65, 75, 85, and 95. And the y-axis is how often you're right. And then the closer the dots are to the line, that means you're more well calibrated. It means that when you're 55% sure, you are right approximately 55% of the time, and so on. So that's the final step. So if those of you who are done marking, you can move on to that. Okay, that's most people. Maybe we'll stop there. So how many of you are done? Looks like most of you, including the line thing. Okay, so like I said, this is a way of looking at how well calibrated your confidence is. If the dots are close to the line, that means that when you are X% confident that something is true, you're right approximately that percentage of the time. So I start with these examples because the biggest hurdle for people to get over with Bayes' theorem is often not the math. It's just wrapping their head around the idea of having a level of confidence, making bets, and the idea that it can be mathematized. But once you accept that you can have a level of confidence that can be quantified, Bayes' theorem follows pretty trivially from a few very basic assumptions. So let's do the fun part and walk through the equation. So I'll start by walking through it conceptually, and then I'll give two examples of it in practice. One physical example, and then one hypothetical example. So the thing we want is this. This is the thing we get at the end, the probability of the hypothesis given the new evidence. So it's some particular piece of evidence that you've received. And what you want to know is, does that piece of evidence increase our confidence in the hypothesis or decrease it? And this is how you find it. So the line just means given. So it's the probability of this given this. So the first thing is probability of the evidence given the hypothesis. So the terms are reversed. What this means is if the hypothesis was true, we don't know if it is, but just if it was true, how likely is it that you would see that evidence? So the probability of the evidence given the hypothesis. Multiply that by the probability of the hypothesis. What this really means is the probability of the hypothesis given the background information. So before you even look at this new evidence, how likely is the hypothesis? This is called the prior probability. Probability prior to you looking at the new piece of evidence. The term for this part, is the posterior probability. And probability here means level of confidence. You can use this equation for what's called an objective probability, where it's how likely is an event to occur. But here, probability means a level of confidence that you as a subject have in the hypothesis. Now, the bottom looks scary, but this part is exactly the same as this first half. It's just that reproduced there. Really, what this comes down to is x over x plus y. So x appears twice, which is this top part. So that's repeated, and then over here is the probability of the evidence given not the hypothesis, so the negation of the hypothesis, meaning it's not any particular alternative, it's just the hypothesis is false. So if the hypothesis was not true, how likely is it that we would see the evidence that we have? Plus the probability, the prior probability of the negation of the hypothesis. This just means not. I think in the key terms I have the word not, but I put this symbol just to save space. So that just means not. Okay, so now you'll see in the key terms that there are two versions. I will tell you right now, I'll be very nice. This is for free. Memorize this one. You won't have to use it, but you'll have one of the questions is just Bayes' theorem long version. Write it out, free mark. Merry Christmas. So this is the long version. And again, one way to think about it to force yourself to remember is remember that it's x over x plus y. This is the same in both cases. The short version, the top is the same, but the bottom is just probability of E, probability of the evidence. And the reason is, when you think about what these two things are, both of them include the probability of the evidence given something. So what it's capturing is how likely are you to see that evidence if the hypothesis is true and if it's false. In other words, how likely are you to see the evidence just in general? And then on top it includes how likely are you to see the evidence if the hypothesis is true. What you want is the top thing to be big and the bottom to be small. And the bigger the top thing is and the smaller the bottom thing is, the closer it will be to 1. Which is, of course, certainty. Okay, so this all may seem very abstract. Let's go through 2 examples. The first one is a physical example. So I have here on the table 3 things, I guess. I have 2 piles or heaps of markers. Heap 1, heap just means pile, but it'll be easier because then you can remember its age. Heap 1 has this, 3 black markers and 1 blue. Whereas heap 2, actually, I'm sorry, I'm going to move this over just for the video, because I think that might be out of focus. Okay, heap 1, 3 black, 1 blue. Heap 2 has 3 blue, 1 black. And what I'm going to do is flip a coin, and if I flip heads, I will pick from heap 1. If I flip tails, I will pick from heap 2. Okay? So, I flip the coin. So, I'm not going to tell you what I flipped. Now what you are going to do is make a bet, or I'm going to show you how you make a bet using this and the evidence. So, I'm going to randomly pick one from the heap that I flipped. Okay, so this is what I drew. Now, so that's your evidence. Your evidence is a black marker. The hypothesis, let's focus on this hypothesis. Let's say we want to know what's the probability it was in heap number 1, or probability of heads, which is nice as it's H. So what's the probability that it was H, heap 1, given the evidence being the black marker? This is how you calculate it. So one thing you have to know is the probability of E given H. So if I drew from heap 1, what's the probability I would draw a black marker? So someone tell me, what's the probability? 0.75. 0.75. So there's a 75% chance I would get that evidence if I drew from heap 1. What the prior probability? What's that? Before you looked at the black marker, what was the probability I would draw from heap 1?
Is it 0.5?
It's 0.5 because I flipped the coin, right? So there's a 50% chance it was heap 1. So now this, we just reproduce, right? Because this part's the same. So 0.75 multiplied by 0.5. Okay, now what's the probability of the evidence given the negation of the hypothesis? So if I didn't draw from heap 1, I could make this. Let's keep the color consistent. The chances would be 0.25. And then the probability of the not hypothesis, or if not the hypothesis, it has to be 0.5. So the probability of not H and the probability of H have to add up to 1, because they're mutually exclusive. So they have to add up to 1, and that's it. So I don't have my phone with me, but someone calculate. Oh, sorry. This should be a times. So there you go. That's all you need. So someone tell me, with your phone or whatever, what is the probability of H given E? My phone's over there, so I can't use it. I guess I could do it on here. If it sounds wrong, I'll double check. Okay, does anyone have the number?
I got 0.75.
Yep, that's what I got. So there you go. So the answer is 0.75. This one's made to be quite neat. You could almost guess it just from this. That won't always be the case. But yes, 0.75. So there's a concrete, easy to grasp example. But we want also examples of theory testing. So I'll give one other example that's less concrete. So with this one, there's more of a right way to do it because the probabilities are fixed by how many markers I have. But in some cases, you have to start with subjective bet taking, kind of like the examples we saw earlier, and then try to use those. So let's take a somewhat silly example, but it's a kind of hypothesis testing. Let's say the hypothesis is that a UFO visited the Earth. And the evidence is there was a flash of light that moved really quickly through the sky. So E is flash of light in the sky, moving through the sky. So how do we do this? So the probability of the evidence given the hypothesis is, if a spaceship did move through the atmosphere, how likely is it that there would be a flash of light? And there, the probability is actually probably somewhat high, maybe, I don't know, 0.8, if we're being generous to the alien people. And what often happens when people defend crazy views is they focus on this probability and ignore the rest. Obviously, they're not doing Bayes' theorem in their head, but that's often how irrational thinking occurs. They focus on this and ignore the others. They'll say, well, hey, come on, if an alien spacecraft moved through the Earth, there would be a flash of light, right? Even if that's true, we can't stop there. One thing that's going to kill it is this, right? The probability of the event or the hypothesis given the background knowledge, right? Your prior probability, and probably 0.001, or maybe 2 zeros, I don't know, but it would be pretty low. Given the background knowledge, every other time there's a flash of light, it turns out to be like a meteor or something. So before I look at this new evidence, my confidence in the hypothesis that aliens visited the Earth is going to be very low. Not zero, but low. So then, of course, we just reproduce it. 0.0001. Now, probability of the evidence given not hypothesis. This is maybe the most important thing that people neglect. What you're asking here is, how likely am I to see that if an alien didn't visit the Earth? And still probably pretty high. What?
Oh, I'm being biased.
What did you say?
Oh, I would give it a probability of 0.9.
That's maybe a little high. I mean, so you're asking, how likely am I to look up at the sky and see a moving flash of light? Doesn't happen every night. I might give it 0.5. Still high, right? But maybe this is a little higher, who knows? The probability, this is, if there's no spacecraft, how likely is there to be a flash of light through the sky? Doesn't happen every night, but it's still somewhat common. You could quibble about the exact number, but something like that. And then remember, this and this has to add up to 1, so 0.999. And then you do the math. We don't have to do the math for this one, but it's going to be low. Even though this is high, given how low the prior probability is, and the fact that this one's still fairly high, means that it's going to be low. Remember that this equation works out to be x over x plus y. So there's two ways to make this overall thing higher. One is to make x bigger. So if these two together is a big number, that will bring it closer to 1, or this smaller. If it's less likely that you would get the evidence if the hypothesis is false, right, making this number lower, or the prior probability of it as well, one of these two. If those two are lower, that will also tend to make this closer to 1. Okay, and then I have a video of another example, but before showing that, any questions about Bayes' theorem? So in the video, it uses the simpler version where, remember, the bottom part is just the probability of E, which makes sense because, remember, this includes how likely the evidence is given the hypothesis, and this includes how likely the evidence is given the hypothesis being false. So overall, it's the probability of just the evidence occurring in general. So we've got the lights. This will have another example. Okay. So another term I forgot to add, it's in the key terms. So this is the prior probability of the hypothesis, prior probability of the negation of the hypothesis, the probability of the hypothesis given the evidence, or the posterior probability. The other terms are likelihood, which is sometimes used synonymously with probability, but it's actually the term for these two things. So the probability of the evidence given the hypothesis or given the negation of the hypothesis. So they're sometimes called the likelihoods. So how does this help us with philosophy of science? So most philosophers of science who use this are taking what the book calls a subjectivist approach to probability. Subjectivist, not meaning like, oh, it's all subjective, bro. Just meaning it's about how confident you are as a subject in the hypothesis. And about how to rationally modify it. The book has a discussion of the axioms of probability theory. I'm not going to go into that in detail. You can have a look at that. The key takeaway is the idea of something called a Dutch book. So the axioms include things like, the probability of H and the probability of not H should add up to 1 if they're mutually exclusive. Things like that. So just very basic assumptions you need to derive this. And someone may ask, well, I don't like these axioms, bro. I don't accept these. And what the book says is, if you don't accept these axioms, you wind up in a situation where if you make bets not following the axioms, you are guaranteed to lose money. So the book has that's a Dutch book. If you make bets in a certain way, wrong way, where you don't follow those axioms, you are guaranteed to lose money, which is not good. So unless you want to be guaranteed to lose money, you should accept the axioms from which this is derived. So far this all seems pretty good, but this is a philosophy, kind of philosophy class. There's always going to be problems. So the difficulty is in setting these values before you see if the evidence is there or not. And there's not, even there is a rule, this is the rule, for adjusting your confidence levels after getting the evidence. There's not a clear rule for setting values like this and this. That you do before you do your little calculation or your little experiment, and there's not going to be a clear rule for that, especially in the case of the likelihood. So take Darwinian evolution. Let's say the hypothesis is Darwinian evolution, and the evidence is some fossil thing. I don't know, Lucy. So Lucy's this fossil of something that looks like neither like a human or a chimpanzee. So let's make the hypothesis right. Let's say the hypothesis is common descent between humans and chimps. So you have to put a number in here. How likely is it that we would see this fossil if evolution was true? There's not a rule for doing that, right? You kind of have to just say it's going to be about your confidence levels. The book talks about the idea of convergence, which is the idea that you can set up these models of what will happen when two different agents get more and more evidence, and you can show that given certain assumptions, with enough evidence, two people, if they're following Bayes' theorem, will eventually converge on the same belief, which is nice, but they assume things like, they give the same likelihoods to given pieces of evidence. So if two people disagree about evolution, the only way you can get them to converge is if they give an equal value to, how likely is it that we would see this fossil if evolution was true? And that's perhaps a generous assumption. So that's the shortcoming, because one thing you may wonder is, the whole reason we arrived here is because of the problem of induction. So remember the kind of journey we went on with regard to probability was induction and confirmation have all these logical problems. So the way to solve those, according to Popper, is to not talk about confirmation and just talk about disconfirmation, which you can cash out deductively. But then we thought, well, with Popper, you can't say anything about what you think of a hypothesis that has been successfully tested, that has passed the test, all you can say is, well, it hasn't been falsified yet, which you want to be able to say more. So we've gotten here. So is this a solution to the problem of confirmation or of induction? And in a certain sense, no, just because probability is built in at the beginning. It assumes this kind of probabilistic notion of how confident you are in a hypothesis. So probably you will still have to fall back on something like a Humean idea. So remember that Hume, who put forward the problem of induction, his solution was that induction and probabilities and things like that are just features of kind of animal instinct or habit. They're things that we have levels of confidence in ideas because of the kinds of creatures we are. All this does is it enables us to do that in a consistent way. That's what it enables us to do. So we just take for granted that we have confidence in hypotheses of different levels, and this allows us to do it in a way that where we're not contradicting ourselves. But it's still at bottom subjective bet making. Okay, so some possible connections to practice in psychology and some other implications for the philosophy of science. So in relation to Popper, there's two different things you could do with Bayes' theorem. One is you could say, Bayes' theorem is how we will cash out our confidence in a hypothesis when it's been corroborated. You could have Bayes as kind of an add-on to Popper. So you could agree with Popper and say, look, when we disprove a theory or falsify a theory, that we can cash out with deduction. Don't need any of this Bayes business. You can, at least if you have certain background assumptions, you can cash out falsification deductively. But when we want to say how confident we are that evolution is true, in the case of a good theory, we can say, well, we'll use Bayes. That's one option. The other option is you could say, forget about Popper. Deduction isn't what we're doing anyways. We saw some problems with that, and we can do Bayes both for confirmation and disconfirmation. That is where some people go. Another thing that helps us cash out is the idea of a damn strange coincidence. So we didn't make this precise. So this is the idea that a confirmed prediction is more impressive if the successful prediction would be a damn strange coincidence if the hypothesis were false. So remember my snow example, right? So if I have a theory and I derive the prediction from that theory that it will snow at least once in January, no one's going to be impressed. If I predict the exact days and times, people are more impressed, because that's more of a damn strange coincidence if my theory is false. And here's a way we can make that more precise. It's a damn strange coincidence if this is low, right? If it's unlikely we would see that evidence if the hypothesis is false. Remember, making this lower makes this bigger, right? If you make this part smaller. So in the case of the snow example, if I predict the exact days and times that it will snow, it would be very unlikely that that I would get that right if my hypothesis is false. That's a way to make this idea more precise. And then finally, three connections specifically to psychology. I won't test you on these. These are more so for those of you who want to go on into graduate school or are interested in these kinds of things. One thing I will say is there is a growing, an approach that's growing in popularity, which is to get rid of null hypothesis significance testing with like p-values and all that. You can actually use this, there is Bayesian statistics. So not just as a general theory of how confirmation works, some have actually used this to make a different way of doing statistics. SPSS has it now. I have a friend who works in biostatistics, and it's what he uses. So that's one concrete application. Additionally, there's something called Bayesian predictive coding, which is increasingly popular. which is an attempt to model how the brain works by assuming that it's engaging in this kind of thing. So in visual perception, say, there's such a thing as top-down processing, as I'm sure you all know, and there's a way to model that where the top-down is like the prior probability of a hypothesis. So, you know, if you're looking at an object, you have a set of experiences with objects that look like that, and you can then impose that on the incoming sense data. So we're not going to spend too much time on that, but I just flagged that as this is another application of this. Well, I guess one thing I forgot to say, which is relevant to that, this is in the key terms. There's a saying in the book, today's posteriors are tomorrow's priors. So once you calculate this, this is the posterior probability. The next time you collect a new piece of evidence, whatever this you calculated to be, it now goes here, right? Because now you have new information, and that will serve, this number will serve as the prior probability the next time you collect evidence. Does that make sense? Yeah. And you can do the same thing when modeling how the brain processes new evidence or new information. And one final piece of relevance for psychology is that I just got this in a review. There's a paper I'm trying to get published on confirmation bias, and one of the reviewers said, confirmation bias might not be a bias. I was like, what? And there's a new paper just published on this, because if you're a Bayesian, taking your prior belief in how likely something is and using that to inform how much credence you put in new evidence, you're supposed to do that. That's called just using the prior probability. So I was like, whoa. So confirmation bias, at least a certain version of it, may not be a bias. So that's one potential implication. Obviously there are versions of it that would be irrational even given Bayes' theorem, but that's another interesting consequence. Okay, so to wrap up this section though, I have another video. So the example I gave, like that activity we did, is from Julia Galef's book. Julia Galef is a hardcore Bayesian. She writes a lot about it and does lots of videos of it. So, leaving aside the math, what's the practical takeaway? So I'll show a video of her explaining that. Then I'll just say a few more things. Okay, so that's well said by Julia Galef. Her YouTube channel is great if you want to see more about Bayes' theorem and other issues. I'll note, it was a very sad day in my life when I found she was married. No, but her channel is great. And her book, Scout Mindset, also great. Discussion of Bayes' theorem. Okay, so that is all of the content that you need for test number 1. So I just want to say some things in closing. So with this first half of the course on philosophy of science, I hope that I've given you some kind of thinking tools for thinking about how science works and what it means to say this is evidence for or against a theory. I think there's good insights to be taken from all the different perspectives, even the ones that probably are wrong, like positivism, and I've tried to, at various points, highlight what those are. In the next section, philosophy of mind, that's arguably less true. It's kind of have to pick sides in a lot of cases. Like, do we have immaterial souls? Are atoms conscious? Things like that. It's less true that you can kind of take bits and pieces from different perspectives. In some cases that might be true, but I'm not saying you specifically have to take a view in your answers to the test, but these are more zero-sum, the debates that we'll see in philosophy of mind. Having said that, any questions about today's content? Okay, good luck studying for the test. As I say, try to test yourself on the terms before Wednesday, which is test review day, and Friday is the test. All right, enjoy your weekends.